everybody. This little video describes a new method for dealing with missing data that I'm very excited about. It's called fully Bayesian analysis, and it's actually been around for a while. As a matter of fact, it was described in Joe Schaefer's famous book on missing data, published in 1997 under the name parameter simulation. But it's only recently that this method has been available in good and easy to use software. And that's got me particularly excited about it. I think in many ways it is an ideal method for handling missing data for many, many applications. And I just wanted to share with you what I have learned in just the past few weeks about fully Bayesian analysis. So I am now going to share my screen, and we can begin. Okay, so as I said, fully Bayesian analysis is not yet widely used, but there are many attractive things about it that seem to me to make it, in many cases, better than either maximum likelihood or multiple imputation. First of all, it has a strong theoretical foundation. And in that sense, it's similar to maximum likelihood, as well as to multiple imputation that is based on the multivariate normal model and the MCMC method. In that sense, it's unlike the FCS method, which really has no theoretical foundation at all. It just seems like a good way to do it. And simulations tend to support that, but simulations can only cover a very tiny fraction of the potential applications and conditions. Secondly, as I've said, the software that has been recently developed is freeware, and it makes it very easy to implement this method. Third, it can handle a wide range of models and data types. So with respect to data types, it can certainly handle continuous variables, but it can also handle categorical variables, both ordered and unordered, count data, survival data, etc. And it can estimate lots of different models for these various data types. And in particular, unlike multiple imputation, you don't have to worry that your analysis model, your substantively interesting model, is in some way incompatible with your imputation model, because everything is done under one model. And in that sense, it's similar to maximum likelihood. Compared to multiple imputation, it's a lot more straightforward. You simply specify your models, and you get your, let it run, and you get your results. You don't have to go through this process of producing data sets, analyzing each data set, and then combining the results. However, it's important to note that this approach also produces imputations as a byproduct, and it does it for whatever kind of model you specify, regardless of how complicated that model might be. And finally, this approach is valid for statistical inference in small samples, whereas maximum likelihood and multiple imputation rely on asymptotic theory, which means that they are valid in large samples, but we don't know how well they're doing in small samples. But the fully Bayesian method is completely appropriate for small samples. Now, there are a few things I need to warn you about. To use this approach, you've got to be willing to think like a Bayesian, both with respect to doing the analysis and interpreting the results. And some people may not feel comfortable with that. I used to be very suspicious of the Bayesian approach, but I've gotten more and more comfortable with it over time. And this new methodology makes it even more attractive to me. Secondly, this approach does depend on the Markov chain Monte Carlo algorithm. And it's important to monitor the behavior of that algorithm and look at evidence that it has either converged or not converged. So you've got to be careful about that. Thirdly, it may take substantial computer time, although it's not yet clear to me whether it's more than you would need for a comparable study with multiple imputation. It may take less computer time than maximum likelihood for very complicated models. Okay. So, as I said, this approach depends on the Markov chain Monte Carlo algorithm, and we already looked at that in some detail when we were looking at the method of multiple imputation. And that algorithm is based on Bayesian theory, and in fact, it is the workhorse of the vast majority of applications of Bayesian analysis with or without missing data. When we used this algorithm previously, we relied on the assumption that the data have a multivariate normal distribution. Okay, although we're going to see that we can now relax that to use the MCMC method with much more interesting and complicated models than the multivariate normal. As we saw before, MCMC is an iterative method. That is, it repeats the process over and over again. And at each iteration, it produces both new imputed values for the missing data and also new estimates of the model parameters. When we used it for multiple imputation, we only obviously focused on those imputed values. But for a fully Bayesian analysis, instead, we focus on the parameter estimates. Okay, and if the MCMC algorithm runs for 1,000 iterations, you're going to get 1,000 different estimates of the parameters. Each of those sets of parameter estimates can be regarded as a random draw from their posterior distribution. Okay, and for Bayesian analysis, the posterior distribution is what you want and tells you everything you need to know about your estimation of the parameters. The collection of all those parameter estimates is an approximation to the posterior distribution. And of course, the more iterations that you get, the closer that approximation is going to be to the true posterior distribution. Now, typically, we want point estimates of the parameters. And for those, we can either calculate the mean or the median of that posterior distribution. So you just take this set of estimates and calculate the mean or the median, and there's your point estimate. What about confidence intervals? Well, in Bayesian modeling, you don't have confidence intervals. What you have are credible intervals. Okay, and to get those, we just take the 2.5 percentile and the 97.5 percentile of that posterior distribution, and those are our lower and upper bounds of the credible intervals. And these have a direct interpretation as the probability that the true parameter falls within the range of those two values. Now, the problem with conventional MCMC software for multiple imputation is that the parameters that are used in the model, typically the multivariate normal model, are not the parameters that we want to estimate. So under the multivariate normal model, the parameters are the means, the variances, and the covariances of the variables in the model. It is possible to convert those into linear regression coefficients, but the standard software for doing multiple imputation has no capability of doing that, although you could probably write a program to do it. Maybe. On the other hand, if the model that you really want to estimate is not a linear model, something as simple as a logistic regression model, these parameters, the means, variances, and covariances, are not going to tell you anything useful. So you can pretty much abandon that approach. However, the software packages that I'm going to tell you about makes it easy to do MCMC for many popular generalized linear models. And generalized linear models are models that include linear models, but also include logistic models for binary ordered or unordered categorical variables, probit models, count data models, and even survival models. Okay. Now, this approach has been available for years in very general Bayesian packages, and that includes packages like WinBugs, STAN, or ProcMCMC in SAS. But those packages are fairly difficult to use for novices, and that includes me. And I wouldn't even attempt it unless I had a lot of time and energy to do it. On the other hand, these new freeware packages are MDMB, which stands for Missing Data Maximum Likelihood Bayesian, and it'll do maximum likelihood analysis as well. This is a package for R developed by Robich and Ludke. But the one I'm going to focus on is BLIMP3, which can either be used as a standalone package, or it can be used as an interface to the R package. And BLIMP3 was developed by Brian Keller and Craig Anders. BLIMP3, compared to MDMB, is much more complete in terms of the range of models that can be estimated. To me, it's a very polished package, user-friendly, and has very good documentation, unlike MDMB. And so we're going to focus on BLIMP3 here. Before we take a look at that, I need to tell you a bit of theory. In particular, I need to talk about factorizing the joint distribution, which was really the breakthrough that made this kind of analysis possible. So one thing we know about MCMC is that to implement it, you need a model for the joint distribution of all variables that appear as dependent variables and all variables that have missing data. Okay. Now, what do I mean by that? Let's suppose that we've got 4 variables, y1 through y4, and they are either dependent variables. Well, let's say y1 is a dependent variable with complete data. Y2 is a predictor variable with missing data. Y3 is another predictor variable with missing data, and Y4 is a third variable with that's a predictor and has missing data. And we may also have exogenous variables that are never dependent variables in the model and that are fully observed, that is, have no missing data. And we can refer to those collectively by the vector x and call that a vector of exogenous variables. Now, in order to do MCMC with these variables, we need their joint distribution, and we can write that in abstract form as follows. F here is a conditional density for y1, y2, y3, and y4. Now, if these were all dichotomous, this would actually be a probability. That is the probability that y1 takes on a particular value, y2 takes on a particular value, and similarly for y3 and y4, conditional on x. Okay. So that's what we would need for MCMC. But the problem is coming up with a reasonable multivariate distribution for those 4 variables. And as we've seen, most multiple imputation software assumes that it's multivariate normal. But we're going to get around that limitation by factoring this distribution as follows. So just using the definition of conditional probability, we can factor this joint distribution like this. So the joint distribution is equal to the conditional distribution of y1 given y2 through y4 and x, the conditional distribution of y2 given y3 and y4 and x, the conditional distribution of y3 given y4 and x, and finally the distribution of y4 given x. So instead of a single joint distribution, we've got the product of 4 conditional distributions. Each of these 4 conditional distributions can be specified as a generalized linear model. So for example, maybe y1 is dichotomous. And typically this would be the distribution, the conditional density that we would be most interested in. So this is our functional model, or I should say our analysis model. And then these are kind of auxiliary models that we need to specify in order to make this work. So if y1 was dichotomous, this could be a logistic regression. If y2 was continuous, this could be a linear regression. If y3 was a count variable, this could be a negative binomial regression, and this could be another logistic regression. Okay, so there are lots of possibilities here. In order to implement this, you need a somewhat more complicated version of MCMC than is usual in multiple imputation software, but it's not a lot more complicated and easily implemented. Okay, well, we're going to see how to implement this kind of thing in Blimp Studio. Blimp Studio is the standalone version of Blimp 3. And we're going to use it to reanalyze the NLSY misdata that we worked with previously when we were looking at the fully conditional specification. Now, what we want to do is estimate a regression of antisocial behavior on a bunch of other variables. Okay, and by the way, this is a sample, just to refresh your memory, this is a sample of children where we've got measures of antisocial behavior, self-esteem, poverty, the child's age, whether or not the mother was divorced, child's gender, mother's age, whether the mother was working in a particular year, and the child's race coded 1, 2, and 3. Okay. And so let's go through some of the code here. And by the way, if you've ever used M+, the standalone version of Blimp has a syntax that is very similar to M+. I think, in fact, I'm quite confident that the authors of this software used M+ as a model. So we've got a number of commands here, and they're all written in uppercase just to make clear that they're commands, but in fact, Blimp is not case sensitive. So everything could be in lowercase, everything could be in uppercase, and it wouldn't make any difference. Okay, each command has to start at the beginning of the line. It's followed by a colon, and then you've got various specifications here. So in the data command, we have to tell Blimp where to find this data set. This particular data set is a text data set, specifically a comma-separated value. It uses periods for missing data. There are variable names in the first row. Now, if your data set doesn't have variable names in the first row, there is also a variables command that could be put right here where you assign names to these variables. And the missing data code can be anything you want. But here we use a period similar to SAS or Stata. In the ordinal command, we specify any variables that are either dependent variables or variables with missing data that are categorical, either binary or ordered. Now, both of these are binary, poverty and mom work. Okay. Then the fixed command specifies predictive variables that have no missing data. So these variables never show up as dependent variables, and they don't have missing data. This command is actually not essential, but it can reduce computation time if it knows in advance that these variables don't have to be part of the imputation process. And then the nominal command is for variables that have more than two values and are not considered to be ordered values. And this particular variable has values, I think, of 1 for non-Hispanic whites, 2 for Hispanic, and 3 for blacks. You have to tell BLIMP what value in the data set corresponds to missing data, and that's the period. And then we specify a regression model. Okay, now, like R, it uses the tilde to separate the dependent variable for the set of independent variables. Okay, now later on, we're going to specify the relationships among these variables, but for now, we're just going to specify this single equation here. We need a seed number, which could be any positive number. And it's important to have a seed number so that you can replicate this if necessary. Burn is for the number of burn-in iterations. So that's how many iterations it runs before it starts to collect the parameters. And then the iterations specify how many iterations after the end of the set of burn-in iterations. So here I specified 10,000. Okay, now that may seem like a lot, but this runs remarkably fast, less than a minute, certainly, to do this. Okay, notice that each command is concluded with a semicolon. Again, that's similar to M+. Now, by default, we assume that all the variables on this side of the equation that have missing data are multivariate normal, which seems contrary to what I just said about factorization. But that makes things easy, and we can easily make them more complicated if we want. Now, ordinal and nominal variables are treated as categorized versions of latent normal variables. Okay, and this is much better than simply rounding imputed values or some other method, and it's essentially equivalent to treating those variables as being related to other variables by probit models. And it works well for most applications, but we're going to see how to modify that in just a moment. Okay, what do we get from this? Well, here's a portion of the output from BLIMP. Now, there's a lot of other stuff, but this is the key thing that we would be interested in. So basically what you would usually get from a regression model, you get a set of coefficient estimates and also an estimate of the residual variance. Okay, now it says median up here. So what this is the median of the posterior distribution. So again, it's got 10,000 parameter estimates here, and it's just taking their median. All right, that's the default. You can override that and request the mean if you prefer that. But the median is particularly good if the posterior distribution is skewed, as it may often be in small samples. Okay, then we have standard deviation. That's the standard deviation of the posterior distribution, and that is roughly equivalent to standard error that we get in a frequentist analysis. Then we get these credible intervals. Okay, and they're like confidence intervals, except they have an easier interpretation. So what we can say is that there is a probability of 0.95 that the true coefficient for self-esteem falls between minus 0.109 and minus 0.025. And that does not include zero. So we could say that we've got significant results at the 0.05 level here. Although, again, this is not a frequentist analysis. We do, however, also get a chi-square test. It's described as a Bayesian wall test developed by Asparuhov and Mutane, who are the key developers of M+. And we get a p-value associated with this chi-square statistic. Each of these is a 1 degree of freedom chi-square. Okay, so all the usual stuff for regression output, but a somewhat different interpretation. These results are very similar to what we got earlier when we applied the FCS method to impute the missing data here. Now, one of the things that I particularly like about BLIMP is that you can use it from within R. And here is the R code for doing exactly the same thing that we just did in BLIMP Studio. Okay, so we need to download and install a package called RBLIMP. Okay, and then I'm using the Rio package to read in a SAS data, a stated data set, the NLSY and store it in a data set called NLSY. So this reads in a stated data set that has variable names, and it converts the missing values to NA, which is what R expects for missing values. Then here's the RBLIMP function. And each of the arguments in that function corresponds to one of the commands that we saw in BLIMP Studio. So we've got a data argument where we specify the name of the data set, ordinal equals, and then in quotes, the two variables that we want to specify as ordinal, nominal equals race in quotes. So all of these things have to be in quotes. Here's our fixed variables. Here's our model. And we specify the same seed number, same burn-in number, and the same number of iterations. And then to actually see the results, instead of using the summary function, we use the output function applied to the output object for NLSY out. Now, in order for this to work, BLIMP has to be installed on your computer. What this code does is that it sends those commands to BLIMP. BLIMP actually runs the model, so it's not using our computation algorithms. Then it sends the results back to R. So the output object, NLSY out, contains almost anything you might want, including imputed data sets if you request them. Now, what's nice about that is that R can do further processing on any of the components of the output object here. And there's a lot of things that you might want to do with that. Okay, so that's how to do it in R. Now, the last thing I want to demonstrate or talk about is full factorization. So the model that we were just looking at was only a partial factorization of the joint distribution, and there were two parts. One was the linear regression of anti on all of the other variables. The other part was a multivariate normal density for all the predictor variables with missing data. And as I said, for categorical variables, that implies a probit model for the dependence of each categorical variable on the other variables. Okay, and that's probably good enough, but we can do better, possibly better. So a full factorization would allow you to use logit rather than probit for the categorical variables. It would allow you to include interactions and other nonlinearities in each of the regressions that make up the model. And very importantly, you can incorporate latent variables with multiple indicators into the models. Okay. So we're going to use this with the NLSY MIS data. And here's the BLIMP Studio code. I'm not going to show you the R code because that should be fairly straightforward from what we just saw. So again, we're reading in the same data set, specifying the same ordinal variables, specifying the same fixed variables. So everything is the same up to our model. And I've also used the same number of iterations down here. So we've got our main model of interest, anti-regressed on everything else. Then I have a logistic regression of poverty on the other predictor variables. I've got a logistic regression of mom work on the other predictor variables except for POV, okay, because mom work was already affecting POV, so you can't have POV also affecting mom work. Then I've got a multinomial logistic regression of race on the remaining variables, excluding POV and mom work. And finally, I've got a linear regression of self-esteem on these variables, excluding POV, mom work, and race. Okay, so this is a full factorization of the joint distribution among this set of variables. BLIMP is going to give you estimates for each of these regressions, although you may only be interested in the first one. Again, these other regressions can be regarded as just auxiliary regressions to produce a joint distribution for all of these variables. Now, this takes a little more time to run, but not much, and it gives results very similar to what we got with the partially factorized model that we looked at earlier. So I'm not even going to bother displaying the results. They're so similar. The ordering of the predictor variables is arbitrary here. In other words, I could have started out with self and then gone to other variables. I could have completely changed the ordering of these variables. It does make a difference in the results, but typically very little difference. Okay, but if you're concerned at all about the arbitrariness of this ordering, you can try out different orderings and see if it makes a difference. Only rarely will it make a noticeable difference. Okay, finally, here are some other features of BLIMP3 that I will just mention. You can do path analysis, so you can do multiple equations with mediating variables, for example. You can do structural equation models with latent variables. In fact, most of the models you could estimate with M+ can be estimated with BLIMP3. You can do multi-level models with random intercepts and slopes up to 3 levels. If you have skewed variables that you don't want to treat as normal or approximately normal, you can do a Yo-Johnson transformation that estimates the parameters of that transformation from the data. You can include auxiliary variables very easily for improving your handling of the missing data. Now, in order to do any kind of Bayesian analysis, you have to specify a prior distribution. And BLIMP3 has several different non-informative prior distributions that it uses as defaults. But there are alternatives, and you can specify informative priors if you so choose. Interestingly, you can, as you said, you can estimate latent variable models, but one thing you can do that's very difficult to do with most latent variable packages is that you can have interactions between 2 latent variables in their effects on some other variable, or between a latent variable and an observed variable. Something that's hard to do with most packages. You can do it with M+, but it's not straightforward. If you believe that your data are not missing at random, and again, the default is to assume missing at random, you can estimate selection models or pattern mixture models within this general framework. Another nice thing about BLIMP3 is that if you've got multiple cores on your computer, it will automatically do parallel processing with all available cores to greatly speed up the computation time. And lastly, and importantly, you can have combinations of all of these things. Okay, so a lot of packages might allow you to do this, but at the same time, you couldn't do this. All right, but all of this can be done within one general framework. And that's basically it. If you want to learn more about BLIMP3, just type BLIMP3 into Google and you'll go to their website. There's a long user's guide. There's information on how to download it. And I say, give it a try. It might change your life in terms of dealing with missing data. Thanks a lot. I hope you enjoyed this little supplement to the course.